Hello, future engineers. This video presents 5 solutions to 2D frames, part 1. So the principles on frames are simply the correct construction of free body diagrams, and the technique is called method of members. So we have to draw the free body diagram of the whole part or the interconnected parts correctly, and from there we write equations of equilibrium. 3 equations of equilibrium are available: summation versus x0, y0 or vertical 0, and summation of moment about any point 0. Then aside from that, it is also important to find members that are two force bodies. So level 1 problem: determine the components of the reactions at A and E if a 750 Newton force directed vertically downward is applied at B, then letter part B at D. So if the 750 Newton downward force is directly applied at B, then CE, member CDE, is a two-force body because there's no load in between. So remember the principle of two-force body: the forces at the pins will be directed to each other and collinear, equal also. So this is the FBD. At A, we expect two reaction components also at E, but we simply replace the reaction at D by a single force which passes through C because it is a two-force body as shown. Then the angle here that RE makes with the horizontal is arctan of 75 over 250, 170 plus 80. So the angle is 16.699 degrees. So to solve for EH, we set moment at E0, then counterclockwise positive, so EH times 200 mm, then minus 150 times 80, 750 times 80. So EH can now be solved. If it is positive, that's correct. Remember, these are external reactions, and in the free body diagram, that would be final if positive. So 300 newtons leftward, then we cannot solve EV, so we solve for RE first. We set moment A0 or R horizontal 0 to solve for RE. So RE cosine of 16.699 degrees minus EH, which is 300. So RE can now be solved: 300 over cosine 16.699 degrees, 312.21 newtons. So therefore, E horizontal is RE cosine of 16.699, the horizontal component of RE, and it is rightward. So R sub EH is equal to 300 newtons rightward. So that checks. If you consider the whole system, then summation forces horizontal is 0. Then E vertical is RE sine of 16.699 degrees. So E vertical is equal to 90 newtons upward. Finally, set vertical component of resultant 0, whole system. So REV vertical, which is AV, equals E sub V, which is 90, plus E sub V, then minus 750. Substitute the value of EV, which is 90, so 0 equals 90 plus A vertical minus 750. So A vertical is 750 minus 90, so it is equal to 660 newtons upward. So that's it. That's the complete solution to this problem. Then for part B, not yet finished. So 750 is now acting at D. So this time, it is member ABC, which is the two-force body. So the component reactions at D, let's assume the direction shown. And also, do not just assume, you just anticipate the direction. Anyway, if you do not think of that, then you just put two reaction components, then just analyze. Then if they are positive, the direction, assigned direction should be correct. If negative, then you just reverse it. But make sure that the static equation is correct. So this time RA is a, or member AC is a two-force body. That's why the reaction at A passes through C. In the same manner, the reaction at C passes through A. Then the angle here is now, with the horizontal, is now arctan of 125 over 250. It is equal to 26.565 degrees as shown. So to solve for RA, we set moment E0. So there are two components, horizontal and vertical, but the vertical component passes through E, so only the horizontal component. Counterclockwise positive, so this is RA cosine of 26.565. The moment arm is again 200, then minus 750 times 80. Then we can solve RA with magnitude 335.41 newtons. So that the horizontal component of reaction at A, EH, is leftward. It is equal to 335.41 cosine of 26.565. So AH can now be solved. It is equal to 300 newtons leftward. Then A vertical is RA sine of 26.565. So 335.41 sine of 26.565. It is upward and it is 150 newtons. Then RH0. So EH equals EH minus R minus AH, which is 300 leftward. So AH is also 300 but rightward newtons. And finally, R vertical equals 0. So we have E 150 A vertical plus E sub V, then minus 750. So E sub V is 750 minus 150, so it is 600 newtons upward. So that's the complete solution to this problem. The 48-pound load can be moved along the line of action shown and applied at A, D, or E. Determine the components of the reactions at B and F if the 48 load is applied, letter A at A, letter B at D, and letter C at E. So at A, member BC is a two-force body because there's no load in between and it is bounded by two smooth pins. Then when the load is at D, then it is CF that will become the two-force body. If the load is applied at E, then again BCD is, or member BC is again a two-force body. Therefore, for parts A and C, the answers will be the same when the load is at A or when the load is at E. So for solution, this is for parts A where the load is at A and C when the load is at E, because member BC remains two-force body for that case. So the answers to parts A and C will be the same. So these are the component reactions at F. Let's just assume leftward and upward. Actually, I also anticipate this from the effect of the 480-pound force. Then, of course, because this is leftward, so the reaction should be upward, up to the right. That's RB. It passes to C because, again, member BC is a two-force body for parts A and E. For parts A and C, rather. So the angle it makes with the horizontal is arctan of 5 inches over 16 inches. And that angle is 17.354 degrees. So to solve for RB, we set moment F0. Then there are two components again, vertical which passes through F and horizontal which is clockwise. So clockwise positive, the horizontal component is RB cosine of 17.354 degrees and the moment arm is 12, 5 plus 7, then minus 48 times 8. So from there, RB can now be computed, 33.526 pounds. Then we compute the horizontal component, we call that BH, which is RB cosine of 17.354. So BH is rightward. It is equal to 32 pounds rightward. B vertical can also be computed. RB sine of 17.354 degrees. So B vertical is equal to 10 pounds upward. Then for FH, RH0. So horizontal component here is 32 equals 32, then minus FH. Then FH is also 32 but 32 pounds but leftward. Then R vertical equals 0. Then we have vertical component of B is 10 plus FV, then minus 48. So FV is equal to 38 pounds upward. So that's for parts A and C. For part B, so let's draw the figure because when the load is acting at D, then it is CF that is a two-force body. So the reaction at F will pass through C. Then B will have also two vertical components, two reaction components. So this angle, the measure of this angle is arctan of 7 over 16. So 23.629 degrees. So these are the component reaction assumed. So to solve for BH, we set moment F0 clockwise positive. So BH times 12, then minus 48 times 8. So BH is equal to 32 pounds rightward. Then moment B0 to solve for RF. There are two components, vertical which passes through B, no moment, then horizontal which is clockwise. So clockwise positive, RF cosine of 23.629 degrees times 12, then minus 48 times 8. 48 times 8. So RF magnitude is 34.925 pounds. And we can now compute the horizontal component which is leftward. FH equals RF cosine of 23.629 degrees. So FH is equal to 32 pounds leftward. Then the vertical component is RF sine of 23.629 degrees and it is upward. So for vis-a-vis, R vertical equals 0 equals vis-a-vis, then plus FV which is 14, then minus 48. So vis-a-vis is 34 pounds upward. So that's the complete solution because we solved parts A and C combined for the first part, and the last part is part B. Show that when a frame supports a pulley at A, an equivalent loading of the frame and each of its component parts can be obtained by removing the pulley and applying at A two forces equal and parallel to the forces that the cable exerted on the pulley. Then in part B, show that if one end of the cable is attached to the frame at point B, a force of magnitude equal to the tension in the cable should also be applied at B. So in part A, this system is the same as removing the pulley and applying the tensions at A at the center of the pin and parallel to the applied forces. And in the second part, then we have a cable which is attached to the frame, and it is equal to a tension on the frame plus two tensions applied at A, which is the result of part A also for this part. So for part A, so this is the situation. I can remember axiom of mechanics. You can add any number of force systems in equilibrium without affecting the original system. So I will add two pair of forces which are parallel to this but in equilibrium. So going here and going there. So the original system is not affected. Then another pair of systems parallel to this tension here, but in equilibrium. So adding these two pairs of equilibrium forces cannot change the effect of the original system. Now notice that this T here and this T here constitute a couple which is counterclockwise. So if I remove these two, I can replace them with a couple equal to tension times radius because they are parallel. If the radius of the pulley is R, so counterclockwise, and it is equal to TR. Likewise, this tension that is upward and this tension which is downward will constitute a couple which is clockwise, and I can remove them, replace them with a couple which is clockwise. So this counterclockwise couple and clockwise couple are equal in magnitude, so therefore in equilibrium. So that the remaining four system would be these same tensions acting at the center of the pulley earlier and parallel to the given original tension. So that's why this system is equivalent to that system. So that's for part A. For part B, so we have to cut this cable here and replace it with tensions. So one is acting at B and one is acting at the top of the pulley. Then considering this pulley here, it's like we have tension to the left and tension downward, which is if we follow the result of A, then automatic supposedly, but I need to show by adding two forces in equilibrium again, T to the left and T to the right, and T downward and T upward. So for this T to the right and T to the left, it constitutes a counterclockwise couple. I remove them, replace them with a counterclockwise couple with magnitude TR. Then T downward and T upward will constitute a clockwise couple of the same magnitude but clockwise. Therefore, TR counterclockwise and TR clockwise will just cancel effect. So therefore, what remains is a tension at the center of the pulley leftward and tension downward, which is the same as this, and a tension at B. So that's why this is equal to that system there. So that's it. I hope you understood the explanation and presentation for this problem because we applied this to frames with pulleys. Knowing that each pulley has a radius of 250 mm, determine the components of the reactions at D and E. So considering the system here, we have DH and D vertical, anticipated directions also, then EH to the left, then EV, let's just assume downward also. So take note, this is 4.8 and the radius of the pulley is 0.25 meter. Therefore, the distance of 48 from E vertical and D is 4.25. So ME equals 0, considering the whole system, so that we can solve DH clockwise positive. So equals moment or summation moment is 0. So DH times 1.5 equals DH times 1.5 minus 4.8 times 4.25 because the radius of the pulley is 0.25 meter. So from there we can solve DH, which is equal to 13.6 rightward. Since there's no other horizontal load here in this whole free body diagram, then we conclude that EH is also, summation forces horizontal, is also 13.6 but leftward kilonewtons. Since we cannot solve d sub v and e sub v by this whole system, we draw the free body diagram of the lower portion and applying the principles in level 3 problem. So we have here tension at C because it is attached to this frame member. Then EH and EV will not be changed because these are external reactions. 13.6 leftward and EV not yet solved downward. Then at C we have tension of 4.8, same, upward. Then at A we have tension which is along AB, but yeah, along AV, and 4.8 transferred at the center of the pin at A, like that. And aside from this, there should be pin reactions due to this attached member AD. So we'll just assume that the pin reactions are rightward and A vertical upward. Anyway, it's not important because we plan to set moment at A0 and all these forces are not involved. So this distance is 2.25 because this is already 2, then plus the radius of the pulley which is 0.25, so that's why it's 2.25. So we set moment at A0 so that we can solve E sub V clockwise positive. So equals E sub V times, because the original distance is 4, so E sub V times 4. Then minus 4.8 times 2.25. So from there we can solve E sub V, which is equal to 2.7 kilonewtons, and it is downward. And going back to the whole system, R vertical equals 0, then equals D sub V plus minus E sub V, and minus 4.8. Substitute the value of E sub V, which is 2.7, D sub V minus 2.7 minus 4.8. So D sub V is 7.5 kilonewtons, and it is upward. So that's it. That's the complete solution to this problem. For the frame and loading shown, determine the components of all forces acting on member ABE. So this is member ABE. So let's compute all forces at A, B, and E. So we base the final answers to the assumed directions of the pin reactions at A, B, and E. But E is external and F. So let's assume EH to the left, then E vertical downward. That's the anticipated uh, direction. Then at F, FH to the right, and FV upward. So to solve for E sub V, we set moment F0 counterclockwise positive. So E sub V times 1.8, then minus 12 clockwise times 0.3. So E sub V can now be computed, and that's the final answer. It is positive, so it's correct that it's downward. Then we need FV, or we need the free body diagram of this, but let's just solve FV, moment is 0. So F sub V times counterclockwise positive times 1.8, then minus 12 times 2.1. 1.8 plus 0.3 is 2.1. So F sub V is equal to 14 kilonewtons upward. Just to check. So 14 minus 2 minus 12 is 0. So let's draw the free body diagram of BCD. But before that, let's solve for X sub C. X sub C as to 0.6 equals 0.9 as to 1.8. 0.6 plus 1.2 is 1.8. So X sub C is 0.3. So if X sub C is 0.3, that means this distance from C to center is 0.6, and the distance from center to B is also 0.6. So the distance BC is 1.2. Distance BC is 1.2. So FBD of member BCD, this is N sub C. So B sub V, just assumed but anticipated. Then this is distance C to D is 0.3 plus 0.3, so 0.6. And the angle that NC makes with the horizontal perpendicular to this inclined is the angle between this inclined and the vertical. So therefore, it is arctan of 0.9 over 1.8, and that is 26.565. Again, arctan of uh, zero point 0.9 over 1.8, zero point 0.6 plus 1.2. So 26.565. To solve for B sub V, we set MC 0, or to solve for N sub C, we set moment B 0. So there are two components of N sub C, vertical and horizontal. The horizontal has no moment at B, so the vertical component is counterclockwise. So N sub C sine of 26.565 times 1.2 minus 12 times 1.8. So N sub C can now be computed equals 40.25 kilonewtons. So that moment C is 0, counterclockwise positive, so B sub V equals B sub V times 1.2 minus 12 times zero point 0.6. So B sub V can now be computed but not yet finalized because we transfer it to member AB later. So let's have the direction later. So it is upward at B later. Then we can solve BH if we set our horizontal 0, and it is equal to N sub C 40.25 cosine of 26.565 minus BH. So BH, magnitude of BH can also be computed, 36.00 kilonewtons. Then let's do the FBD of member ABE, and this is FBD of ACE, ACF, and this is for ABD. So let's transfer BH here. Take note, these results are positive, so action-reaction principle, so it's to the right here, and vis-a-vis is upward because the values are positive. Therefore, we finalize the answer for BH. It is 36 kilonewtons and it is rightward on member ABE. So the direction is important in the problem. Then vis-a-vis is 6 kilonewtons upward, and it should be upward on member ABE. So we have left AH, A vertical, and AH. And we can answer that from this free body diagram because there are three unknowns left. And there are still three available equations of statics. So for AV, we can solve AV by setting R vertical equals 0 because vis-a-vis has been found and we have 2 kilonewtons here for vis-a-vis. So R vertical equals 0. So we have AV equals AV plus vis-a-vis minus 2. Substitute the value of vis-a-vis, which is positive 6, so AV plus 6 minus 2. So thanks that AV is negative, so that you will also experience a situation where the direction is wrong. So A sub V is negative 4. So this is negative 4 because I assume it is upward, but the final answer for A sub V is positive 4 but downward. So A sub V is positive 4 but downward kilonewtons. But we use this, when you use this value A sub V in this free body diagram, you should take the sign which is negative 4. So to solve for EH, we set moment E0. Then we have uh, counterclockwise positive. So it is equal to AH times 1.8. By the way, this is 0.3. This horizontal distance between BE, which is equal to this X sub C here, 0.3, and this is 0.6 from B to A center because this is also 0.6. So equals AH times 1.8 plus AV times 0.9, 0.6 plus 0.3 plus vis-a-vis times 0.3, then minus BH times 0.6. is BH times 0.6. So take note that AV must be negative 4 because it is still upward in this figure. So 0 equals AH times 1.6 plus negative 4 times 0.9 plus 6 times 0.3 minus 36 times 0.6. BH is 36. So solving for AH is positive, so it is correct leftward, 13 leftward. Finally, R horizontal equals 0, or summation forces horizontal is 0. So we have BH, which is 36, minus AH minus EH. Substitute 0 equals 36 minus 13 AH, then minus EH. So EH is 36 minus 13. So AH is correct. It is leftward and it is 23 kilonewtons. So that's it for this part 1.